Mr. Davis, you got a haircut.
I got a haircut. You know what's funny is you said that just as I started recording. So when people start to watch this video, the very first thing they're going to hear is, Mr. Davis, you got a haircut.
Nice.
Well played. Okay. So we are looking at a problem that hopefully a lot of you are feeling like you have the answer to. But there obviously is something in here that you're like, I've never heard this term in my life. I don't know what this is talking about. So I wanted to explain this. When you look at this scenario, you've got a guidance counselor handing out questionnaires to students she picked to represent a cross-section of the high school, and she wants them to deposit the questionnaire at the end of school. I don't know if I said it, but it has to do with drug use. And I might have actually read that or not. I don't know. So there's a couple of things that might come to mind as a problem with this sampling method. First of all, you're going to get voluntary response because she wants people to drop it off at the end of the day. And, you know, some people just don't bother to do that. So that's voluntary response bias. Also response bias, a different thing here that says this is a survey about drug use. So it's highly probable that at least some of those questionnaires are not going to be completely honest. So you might get incorrect responses. So hopefully both of your, all of you are thinking that these two are definite concerns. So if that's the case, even though you don't know what this is right now, B and C will be like, okay, I think all the above are valid concerns. Now, just to explain what A is, and this is not in our AP standards, they don't use this language, so this could be an old question that they changed what you're expected to know. This would represent, this counselor sees herself as an expert on what a cross-section of the school is, an expert on this kind of thing. So what she does is she says, I know to get a if I do it randomly, I don't get a true cross-section of the school. So I'm going to pick these specific students. I picked out 100 students, and I want these specific students to answer. So that is not a random sample, it's judgment sampling. And there can be bias in that. So that is what's happening in this. So it's not a random sample, so that's part of the concern. So all of the above are valid concerns, and that's how we would answer this question. So today, because of the limited time, we're not going to do as much as it says here, but our main thing is to learn the two sample t-test for difference of means. Whoops, that's not right. It's a two sample z-test for difference of proportions. Anyways, so I made a typo on that, but anyways, we're going to learn this tomorrow, so we're only off by a day. We're only going to do one of these activities, so let's go ahead and jump into it. The Unit 8 tests will be graded soon, but like I said, I haven't actually gone through and done that yet, but I'm going to get started on that today, and we don't have school on Wednesday, so my goal is to have all the grades put in to get caught up completely by Wednesday. That is the goal. Okay, so now let's look at this. We are looking at a scenario where we've got Black and Hispanic females in STEM programs and non-STEM programs. And there is a concern that Black and Hispanic females are underrepresented in STEM programs compared to non-STEM. So a specific university would like to see if this is true for their population. So they took a random sample of 300 STEM students and found that 12 were Black or Hispanic females. They did a different sample of 500 non-STEM students and found that 75 of them were Black or Hispanic females. So that's good data to have, but does this provide convincing evidence that Black and Hispanic females are underrepresented in STEM programs? And we want to use a 5% significance level. Okay, so the first thing I want to do before we jump too far into this is I want to determine this is a difference of proportions. I've got two different samples that I'm taking. So I've got two different sample proportions and two presumably different proportions. Okay, so I want to determine what P1 and P2 is. I will determine right off the bat that the STEM students are P1. So P sub 1 is going to be STEM. And P sub 2 is going to be non-STEM. And what I'd encourage you to do, because you don't have this question prompt, this problem anywhere, but on a piece of paper nearby, I want you to follow along and copy the stuff down because we're going to refer back to it, but it's not going to be on the screen anymore. So I want to make sure that you guys can follow along. So let's look at what's going on. We decided that P1 is STEM and P2 is non-STEM. So let's figure out, we can just go ahead and do this real quick. Let's figure out P hat sub 1 and P hat sub 2, which in this case, so since STEM is P1, I'm going to be a sample size of 312 for Black or Hispanic. So it's going to be 12 out of 300, which is going to be 0.04. Now the P hat sub 2 is going to be 75 out of 500. And that's going to give us 0.15. You can double check that, but that's what it turns out to be. So our parameter that we're trying to test is P1 minus P2. This is the true population. So actually what this is, the true difference in proportion of Black and Hispanic females in STEM versus Black and Hispanic females in non-STEM. The statistic is just going to be the sample version of this. So P hat sub 1 minus P hat sub 2. And that is going to be 0.04 minus 0.15, which gives me 0.11. Negative 0.11, sorry. So there's a negative right there. I'll just put it up above. Okay. Keep in mind, I could have flipped this around. I could have determined that P1 is non-STEM and P2 is STEM, and I would have ended up with a positive 0.11, and that would change the next thing that we're about to do, our hypotheses. Can anyone guess what our null hypothesis is going to be? I'll give you a hint. We're trying to determine that parameter. What do we think about that parameter?
Is the null hypothesis that Black and Hispanic females are not underrepresented in STEM programs?
There you go. That would be kind of an everyday language to say it. The null hypothesis is that there's no change. There is no difference between them. And the way mathematically we would show that is that the difference in these proportions is equal to 0. But this is essentially saying what you just said, Jacob, that they're not underrepresented. All right. And that's a good, actually, I'm glad you said that because that's a good thing to point out. If these proportions were the same, there wouldn't be underrepresentation, but our alternative hypothesis is that, what do we think is going to happen to this difference? So which one's it going to be? That difference is going to be greater than 0, that difference is going to be less than 0, or that difference is going to be not equal to 0?
Less than?
Less than. Okay, and why less than?
Because we're testing to see if Black and Hispanic females are underrepresented, not over.
Right, and to be careful on this, I could have phrased it differently where we would still be testing the same hypothesis, but I'd be using greater than. But specifically, it's going to be less than here because we defined P1 as STEM and P2 as non-STEM. So if women, Black and Hispanic women are underrepresented in STEM, then we should see P1 be less than P2. And if that's the case, a difference between those two is going to be negative. But if I remember, if I had flipped these two right here and just called it different, then I'd be looking at a greater than scenario. Does that make sense? Okay, and I'm asking that to the void, but you don't have to respond. If it doesn't make sense, you can kind of flag that and ask questions on it later. Okay, the significance level is 0.5 or 5% rather, so 0.05. Okay, and I believe we're good with everything on this. So hopefully you've been copying some stuff down. You're feeling good about it. We're going to keep seeing the question prompt up here, but we're not going to be seeing the state part of this. And I should add before we move on, this gives you a little bit more time to copy if you're trying to copy anything. This state, plan, do, conclude format that hopefully you're feeling a little more comfortable with, and it's starting to become like a regular thing to expect. The purpose of this is to organize your work. You do not have to follow this format exactly, but what I would love to see as a grader and what AP graders would love to see is a clear progression in your work that says, I'm kind of setting up the problem, I'm thinking through the conditions, I'm working through the work, and I'm concluding with some kind of putting it back in context, what all these numbers mean. So that's really good, as opposed to just this big old jumble of work, and we kind of have to jump around and like, so here's their p-value, there's their conditions, there's their conclusion, so it's not going to benefit you to have a random jumble of work. You want to have a very clear order to it and show everything. So hopefully you are practicing using this kind of a format, though it doesn't have to follow it to a T. All right, let's move ahead. And we're going to name this procedure. So I named it wrong in our setup. This is a 2-sample z-test for P1 minus P2. You could say for difference of proportions. Honestly, the only thing you need to say is the 2-sample z-test. That's going to be clear enough, though this adds a little bit more context and shows that you really understood the problem. Now we know it's this because they give us 2 different samples to draw from. So focus on this 2-sample. So if you're reading your question prompt and you see 2 samples in there, then you should immediately jump to that. All right, so let's check our conditions. Okay, so first of all, random. So for, I'll do this for both. And the first one, we can see it's a random sample. The second one is a random sample. We're good. 10%. And again, with the conditions, I hope these are really getting ingrained in your memory so that you kind of know what to check every single time. These conditions don't change. The way we check them changes a little bit. And hopefully you're aware of that too. P1 and P2, I need to check both of these. I'm going to assume that this university is big enough that 300 represents less than 10% of all STEM students. And so we're saying that there needs to be at least 3,000 STEM students at the school. If it's a big university, like let's say we're talking about ASU or even NAU, you should have at least that much. Well, NAU is not that small. So yeah, of course, we meet that. 500 non-STEM, which means we need to have 10 times that 5,000 non-STEM students. That's a safe assumption, assuming it's a big enough school. So we're going to assume we met that. And the last one is, are they normal? Now, we're going to learn a little bit more about this later. And what I think is fair to use right here is to go ahead and test this the same way we did with our confidence intervals. So I'll do N1 times P hat 1, and then N1 times 1 minus P hat 1. And those both need to be greater than or equal to 10. All right, and then I will do N2 times P hat 2, and N2 times 1 minus P hat 2. And those should both be greater than or equal to 10. Now, when I multiply this out, I'm going to get 12 and 75 for the first two. So this is going to be 12 right here. This is going to be 75, which means I'm going to get 288 and 425. So we meet this condition and check. I'm being a little bit lazy, not showing the work, but I am confirming that I meet the large counts condition. And also one last thing, remember large counts is only used for proportions. We can't use this for means. That's when we use the central limit theorem or an approximately normal population. Okay, moving ahead, unless there are any questions. Okay, we will come back to the this part of our check, the normal condition, because we're going to see something a little different later. It only changes it slightly. It doesn't like completely change what you might expect. But anyways, we are now going to look at doing the actual calculations. And I haven't actually thrown out what the formulas we're using are, but remember, I'm just going to start right here. We always use this for a test statistic. Stat minus parameter divided by the standard error. That's always what we're doing. So now we just need to figure out what's our stat, what's our parameter, and what's our standard error. And actually now let's kind of go back. That's a minus right here. I'm going to come back up to mean, because the mean here represents our parameter. So if I am going to draw a picture, actually I'm going to change this picture a little bit, make it look. All right, if this is a sampling distribution, just work with me on that. That is representing our null hypothesis. Where does this center? What is the mean of our sampling distribution? So I wrote the null hypothesis in the corner to guide you a little bit. According to our null hypothesis, where should this sampling distribution end up?
Does it need to be greater than 0, the mean?
So the mean is actually going to be right at 0. And so just to explain that, the null hypothesis is that there's no difference between these two samples, and that in reality, there's not an underrepresentation of Black and Hispanic females in STEM majors. If there's no difference between them, then we should get an average difference in our p hat sub 1 minus p hat sub 2. We should get an average difference of 0. So if I took 100 different samples or 1,000,000 different samples from this university, and I kept getting a difference of proportions over and over and over again, it should average to be close to 0. And so the mean of all of these difference of proportions, sample proportions, the mean of all that should be 0. We're not saying that's reality. We're saying that's according to our null hypothesis. That should be the case. Okay, so hopefully that's making some sense for you. The standard deviation, this is where a lot of this is just going to be rinse and repeat. We're going to take stuff we've already learned and just throw it into a new calculation. But there's a little bit of a difference here. And let me kind of show you what you might expect for this. If we're looking at a sampling distribution of proportions, difference of proportions that is, here's what your formula sheet tells you. It's going to be p hat sub 1 times 1 minus p hat sub 1 divided by n sub 1. This looks familiar because this is what we used on Friday for our confidence intervals, plus p hat sub 2 times 1 minus p hat sub 2. Okay, that's all looking good. And n sub 2, I was making sure I didn't make a typo on that anywhere. So that is what it looks like, except that now we have an assumption here we need to keep in mind. So this will be new. And I'll go ahead and tell you, we don't use this. It's going to be slightly different. The assumption is that these two samples are not different. So therefore, what we want to do is we pool our samples together. We're not going to use p hat sub 1 and p hat sub 2. We're going to use what's called p hat sub c, which is combined, also called a pooled proportion. Okay, if you read chapter 22, then this is going to look familiar to you. So the pooled proportion is going to say if we have a certain number of successes in our first sample, and in this case, 12 Black or Hispanic females are considered successes out of the first sample, which was 300. Now I've also got a count which is 75 Black or Hispanic females out of 500 in our second sample. So to combine these, what I want to do is I want to combine our successes from each sample divided by our sample size of each sample. So for us, that's going to be 12 plus 75 divided by 300 plus 500, which is going to be 87 out of 800. And that is going to be, I did this math pretty recently, so I remember it's going to be 0.109. You can just plug that in, double check. So what we're saying is that there really is no difference between these two. And so therefore, the true sample proportion that we should end up with is 0.109. And it's all a part of the fact that we're testing a null hypothesis that says there's no difference. Okay. So for our standard deviation or standard error in this case, we might say, it's really going to be, okay, like this. And I'm about to erase all this, but it's going to be p hat sub c times 1 minus p hat sub c all over n sub 1. Notice that the sample sizes right here in my calculation don't change. I'm still using sample size 1. All right, so p hat sub c times 1 minus p hat sub c. It's going to be the same thing in the numerators for both of these terms, but the denominators will stay as they were before. So n sub 1 and n sub 2 are our two denominators. That's the calculation we want to do for our standard deviation. Okay, so that's the new part of this. I'm going to draw a line to to separate those parts. Okay, so our specific formula. Now it does get a little bit easier. I want to first of all remind you that our parameter is what you would normally do is, remember, it's something like p hat sub 1 minus p hat sub 2 is your statistic, minus a parameter of p sub 1 minus p sub 2. And we get this from our null hypothesis. What are we saying in our null hypothesis that this value is?
Zero.
0. And this will always work out this way, that when you're looking at a difference of proportions, a difference of means, this parameter is 0. So this parameter right here, I'll just X it out. It's 0. So I don't need to worry about it. It's really just the stat divided by the standard error. Okay, so now what I can do to kind of get to the calculations finally, I've got p hat sub 1 minus p hat sub 2 all divided by, and I'm going to squeeze this in, it's not going to look very pretty, p hat sub c times 1 minus p hat sub c divided by n1 plus p hat sub c times 1 minus p hat sub c divided by n2. That's our specific formula for this test statistic. And I can't emphasize this enough. I repeat myself a lot, but I hope that it's helpful to someone out there when I repeat it. You don't have to have this memorized. You just need to know that when you're finding a test statistic, it's this formula right here. And all you need to do is look up, what is my stat for this problem? Oh, it's the difference in my sample proportions. What's the standard error whenever I have a difference of proportions? And this shows up in your formula sheet, though it looks a little different. You can remember it this way, it's just your pooled proportions get replaced. I think that's a little bit easier to remember. Okay, now I'm gonna actually do the work. I'm gonna plug in the values. I already know p hat sub 1 minus p hat sub 2. Well, I didn't, did I? Yeah, I did. It's negative 0.11, negative 0.11. That was a 0.04 minus our p hat sub 2, which was 0.15. So it's negative 0.11 divided by the square root of my combined proportion here was 0.109. I calculated that over here. It's going to be 0.109 times 0.891 divided by sample size of 300. Okay, plus, I get to use the same numbers again. That's 0.109 times 0.891 divided by 500 in my second sample. So I'll let the calculator do the work for the standard error first. All right, so I got 0.0228 is my standard error. And so that means that when I do the division, my z statistic here is negative 0.11 divided by my previous. Is negative 4.83. And I want to go back just a little bit to show that when we're finding this statistic, it's a z statistic because we can have a t statistic also. So I'm going to put right here that this z equals that calculation. And so that's what I end up with this down here. Of course, we haven't answered our question fully yet. We do know that we have a z statistic of negative 4.83. So to interpret this, what we're saying is that we have the sampling distribution. I now know that my standard error right here is 0.0228. So I'm going to go 1, 2, 3, 4, almost 5. So I'm going to have my z sitting right here, negative 4.83. All right. That's where my z statistical is. And I want to see what's the probability of getting that result or something more extreme. That area right there. So this is why you want to have a diagram drawn, because it's going to show you your test statistic is your z-score. The area under the curve right here is your p-value. Okay. So I will They had a spot for this right here, so I'll just put it negative 4.83. Because this is a Z statistic, I can use my normal CDF. Z is your sign to just go ahead and use a normal CDF calculation. So I'm going to go to normal CDF and distributions. And this diagram also helps you remember, if I'm looking for the area below my Z-score, then the Z-score I got is my upper bound. So I'm going to go from negative infinity up to negative 4.83. And I got a p-value of 6.84 times 10 to the negative 7th. And of course, the way you can write that out if you choose is 0.00000684. Your choice on how you represent it. It's going to show a very small number no matter what. So suffice to say, it's highly unlikely that by random chance you're going to end up with a result this extreme. And we can make a conclusion about this. We can, or at least we can say that we have convincing evidence, and we will have a conclusion, but I'm going to clear some space to write out. Well, no, I'm not, because I'm going to go to the next page. So before we move ahead, does anyone have questions on the calculations, the pooled proportion, or anything like that?
You said for the p-value, we use normal CDF?
That's right. And that's because we're looking at, I'll just say for proportions, every time, if it's anything dealing with proportions, you're going to use a normal calculations. If it's means, you're using a T distribution. Okay. So, I mean, that might be just, there's not like a handy mnemonic for that, but I mean, it's a pretty straightforward idea and it always applies. So if you see proportions, you're using normal. If you see means, you're going to use a T. And that's all there is to it. All right, so let's conclude this. All right, I will say because, and this is going to be a format that you've seen before. Though the phrasing, of course, you can change it as long as you get all the information across in a very effective way. Because the p-value was lower than the significance level, and I'm plugging the numbers, so I'll put 6.84 times 10 to the negative 7th is less than 0.05. We reject the null hypothesis. We have convincing evidence that the true proportion of, well, you could say this lots of different ways. I might actually put it in the most simple way we can, because we could talk about the true proportion of Black and Hispanic females in STEM majors is lower than the true proportion of Black and Hispanic females in non-STEM majors at this university. That's a lot to write. So I'm going to put it back into the original context. We have convincing evidence that Black and Hispanic females are underrepresented in STEM majors, STEM programs at this university? All right, and there we go. We have shown an interpretation of the values that we got. We put it back into context, and we answered the original question that are Black and Hispanic females underrepresented in STEM programs? Well, we have convincing evidence that they are. So we answered it directly. There you go. That's about it. That's the process. So I'm going to skip over what the next activity we would have done. And I'm going to jump to this. All right, I'm going to clear the page now. So we have, this is again from the reference posters that I highly encourage you all to download and have available as you're going through practice problems and on the test. So your null hypothesis for difference, and notice it's hypotheses for difference. So proportions, the difference will be 0 for your null every time. And you have to determine if it's going to be not equal, less than, or greater than 0 for your alternative, depending on the problem. The test statistic for difference of proportions. Notice it's statistic minus parameter divided by the standard error. Now they're showing right here, it's a P1 minus P2, but just keep in mind that this is always 0. So this is going to cancel out. So really it's just that value divided by your standard error. And remember P hat sub C, that's given right here. So keep that handy. You only use this for significance tests, and just significance test, hypothesis test, it's the same thing. Even an inference test, you'll hear that referred to. Those are all the same thing. Okay. Right here, when you have conditions to check, this is one thing we didn't do in our problem. And I've seen it both ways, so I'm not sure that you're going to be deemed for doing it a different way. But notice right here, when they're talking about significance tests like we just did, they're even suggesting using your pooled proportion for your significance test. So you're going to take your sample size 1, multiply by the pooled proportion, make sure that's greater than or equal to 10. We used P hat sub 1 and P hat sub 2. I don't know that it actually will matter that much. But it also doesn't hurt you to use the pooled proportion for testing the large counts. So if you are not sure what I'm talking about when I'm going through this, you can stick around. We can kind of talk about it in more detail, but it's up to you kind of how you want to handle it, though it's not up to you to use it here in this calculation. You have to use the pooled proportion for this. So maybe if you're already using it for the calculation, you could use it for the test of large counts. Okay, I'll move ahead. We don't really have time to go through this fully, so I'm going to jump ahead to just the calculations, and there's going to be a lot I'm skipping over, and I'm not going to be doing any of B, C, and D. I really just want to do the calculations here to make sure we have another example. I will just tell you your null hypothesis here is that P1 minus P2 equals 0, and the alternative hypothesis, well, let's read the scenario. All right, so we're talking about men and women buying books online, and we want to see if there is a statistically significant difference between men buying, the proportion of men who buy books versus women. And of course, they phrase it as, is there evidence that men are more likely to purchase books online? Now, there is some anecdotal evidence, you could almost say, because 21% here versus 18%. But if, and I'm going to call for men, P1 will be men, and P2 will be women, just for this purposes, for the purpose of this problem. So if men purchase at a higher rate, then I would expect P1 minus P2. Well, P1 will be greater than P2. And therefore, when I subtract, I should get a positive answer. So my alternative hypothesis is that this difference is greater than 0. All right, so now I'm going to test the hypotheses. I'm going to assume that all my conditions for inference were met. It was random, 10%, and normal. I'm going to skip past some stuff. In fact, I'm just going to jump down here to my test statistic. So it's going to be z equals stat minus a parameter divided by the standard error. I know for this particular problem, it's going to be p hat sub 1 minus p hat sub 2 divided by p hat sub c times 1 minus p hat sub c divided by n sub 1. We still use the first sample size. And then p hat sub c times 1 minus p hat sub c all over the second sample size. Okay, and remember, just to go back to Friday a little bit, this is combining our variances because we're thinking of these as two random variables. So we combine the variances to get our standard error, standard deviation. So p hat sub 1 is 0.21. P hat sub 2 is 0.18. I got that straight from the problem. So here's your p hat sub 1, here's your p hat sub 2. But I need to figure out the combined. And to do this, I need to kind of go in reverse. So I want to do this 0.21 times the sample size, which was 222 men. Notice right here, there's 222 men and 21% of them. So if I multiply that out, I get 46.62. I'm going to round that to 47. All right. For women is 0.18 times 208. If I multiply that out, I get 37 when rounding. The reason I need that is because now I need to do p hat sub c. And that's going to be the combined numbers, 47 plus 37 over the combined sample sizes, which is 430. That's mentioned up at the very top, 430. So now I can get my p hat sub c is going to be 0.195. Okay, I need that before I can move ahead. So I'm using these two values, and I'm using this value right here. And of course, I'm using my sample sizes right here and here. Okay, so now let me plug numbers in. So z is going to equal p hat sub 1 minus p hat sub 2. I can see that's 0.21 minus 0.18, which is 0.03, divided by the square root of 0.195 times 0.805 divided by the first sample size is 222 men, so I'm going to put 222 plus 0.195 times 0.805 and divided by the second sample size, which is 208 women. All right, calculator work at the, no, don't do that. All right. So it's going to be 0.03 divided by something. And I got 0.0382. Okay, and when I divide that, I get 0.785. So my Z statistic right here is 0.785. All right, and just to put this into context, I've got a sampling distribution that I'm comparing this against that says that there's no difference between them. My standard error says that, okay, just by random chance, I'm going to expect a variance of about 4%, specifically 0.0382%. So when I take a sample of 430, essentially, I'm going to expect this amount of variance. And what I ended up with was a sample that ended up right here at about 0.03. And this is my Z statistic. So I want to find out what's the probability of getting that response, that kind of result, or more extreme. All right. So now I can use a normal CDF calculation to tell me. So my p-value is just going to be this area right here, which I'm going to determine from a normal CDF calculation. All right, so normal CDF, it looks like my lower bound is going to be my Z score. So 0.785 up to positive infinity. And I get 0.216. Okay. Hopefully, even if you're not following along in the calculator, you're able to follow along conceptually, though I will say you need to be able to do this on the calculator because you'll obviously have to do these calculations on your own. So we're not going to have time for more examples, and I'm not even going to try and wrap this up with except to kind of start off my interpretation. But I would say something to this effect. Because the p-value ... Okay, so I would finish it this way. Because the p-value is greater than our significance level, and I forgot to even specify a significance level. Well, I'm going to say 0.05. It doesn't matter in this case. Because the p-value is greater than our significance level, 0.216 is greater than 0.05, we fail to reject the null hypothesis. We do not have convincing evidence that men purchase books online more than women. That's what I would write. All right, let me know if you need me to say that again. Okay, so that is the process for a significance test. And the good thing when we go tomorrow, and we, in fact, I'll jump ahead now to this. I'll keep all the writing on the screen just in case anyone's trying to look at it. But read all of chapter 24. We're going to do all of chapter 24 because tomorrow we're just going to be looking at confidence intervals and significance tests for difference of means. So everything that we're doing today, we're just going to repeat tomorrow. Of course, we'll do some confidence intervals. And we want to, or we're just going to see that it's kind of the same process over and over. So, of course, there are small differences for means, like we're using a t distribution and stuff like that. But look through that. You have homework right here, of course, but also I added some more progress checks. So as we are learning this, if you want to run through the progress checks, see what multiple choice questions look like, I highly encourage you guys to do that. And yeah, I don't have anything else to say for today, but if you have any questions, you can feel free to stick around. Otherwise, you get to go 4 minutes early today. Have a wonderful rest of your day, and I'll see you tomorrow.